In this short presentation, we're going to investigate the dual nature of light. Now, one of the fundamental principles of light is that it can act both like a wave and like a stream of particles. And this was really confusing and hard to understand, and is still hard to understand for us today. I just want to go through and show you what we mean when we say that light actually has a dual nature. What do I mean when it say it can act like a wave or act like a particle? So to do that, we're going to examine some wave behaviors and particle behaviors that light shows. So the first thing we're going to take a look at is a wave behavior. We're going to look at diffraction. Now, diffraction is an interference that occurs when a wave passes through an opening or a slit in a barrier that's similar to its own length. Remember, a wave has a length. That's the distance from one crest to the next, or one identical point on one wave to an identical point on an adjacent wave. And so we're going to let a wave go through an opening that has an opening that's similar in width to this wavelength. And when we see that, we'll see that the wave actually bends through that opening. And the most intense spot will appear directly behind that opening. This image was taken from a PhET simulation, and it shows a light source producing light waves, and we can see these light waves are coming out and moving this direction. Now, once they hit this barrier, of course, this wave bounces off and we come back and we see this interference pattern over here where the reflected wave and the incident wave are interfering with each other. But in this opening here, we see that the wave actually makes it through, and we see this wavefront. And as this wavefront propagates through, we see that it spreads out in this curved pattern, and the bright spots of course represent crests, the low spots troughs of this transverse wave. And this is a screen that shows us the light being projected, and just as we suspect, the brightest spot appears right there in front of the opening, and this graph shows that the most intense spot is right here in front of that opening. Now, this isn't really all that impressive. Oh, okay, so we shoot some stuff through an opening and it goes through the opening. Okay, what makes this a wave behavior? Well, it's the interference that occurs if we actually use two or more openings in this barrier. So if we take a look at what happens when we use a double slit instead of a single slit, we're going to see something a little bit different. The waves coming through will interfere, and what we're going to see is the distinct diffraction pattern of waves. So this is definitely a wave behavior. And so you can see this time I have an opening here and another opening here. And again, on the back side, we still have that reflected and incident wave interfering with each other. But on this side, we have this wave coming through and this wave coming through. And you'll notice right here, they interfere with each other, and so we get a bright spot here. And this wave came through a little bit earlier, this wave came through a little bit earlier, and they interfere with each other. And so they're constructively interfering right here, right here, right here, and we get a bright spot directly in front of this barrier, which is odd. If this was particles, we would expect a whole bunch of particles to mostly come through straight, a bunch of particles to come through straight, and we would expect two bright spots of particles here and here. But you can see we actually get dark spots there. We get dark spots because that's where these two waves align and interfere destructively, right? There's some destructive interference. And so light shows this constructive destructive interference pattern, or this diffraction pattern, which clearly demonstrates it has wave-like behaviors. And you guys have all seen light diffract. If you've ever looked at a CD and seen the colors, that's because the groove etched in a CD is very, very close together, and it's on the same scale as light waves. So you can see light diffracting through there. Now, that is just one wave behavior of light. You can also polarize light. That's a wave behavior as well. But now we're going to go ahead and look at some particle behaviors of light. And the particle behaviors were a little bit harder to show, and in fact, Albert Einstein and Arthur Compton both won Nobel Prizes for their work in showing this particle behavior of light. So the first thing we're going to take a look at is the photoelectric effect. Now, you guys are probably familiar with the photoelectric effect. It explains how a calculator works. You get a little photocell in there, you shine light on it, and all of a sudden you've got some electricity. Well, what's actually happening in the photoelectric effect? We're shining a light on a solar cell, and that light ejects electrons, they move through a circuit and come back to the cell, and then the light ejects them around again. So essentially, we are converting the light energy into electric energy. Okay. Now this is known as the photoelectric effect, and like I said, Einstein won a Nobel Prize in physics for explaining how this works. And so the really weird thing about the photoelectric effect is you'd think, oh, well, if it's the light making the electricity, if I just make the light brighter, I'll get more energetic electrons coming off of there, which is not the case at all. Now I want to show you a little demonstration or simulation to show you what I mean. If we take a look at this demonstration, the simulation, it'll show us what's happening. So here we have a battery that's applying a voltage to these two plates that are separated in this vacuum chamber. Okay? This is the positive plate, this is the negative plate. Here's a light shining on the plate. And every once in a while you're going to see that electrons come up off this plate, and when they come off the plate, they come off about, I don't know, a half inch or so. They come just a little bit off the plate. And you'll notice not very many of them are coming off the plate. But I don't have my light on very bright. Its intensity is fairly low. So I'm going to go ahead and turn that intensity up. I'm going to move it up to there, and right away you can see more electrons start coming up off the plate. Okay, you'll notice they're still not coming very high off that plate. They don't have enough energy to get away from that plate to get to the other side. And in fact, they might never make it to the other side the way this battery is oriented, but they're not ever going very high off of that. Now, how am I actually going to change that? How am I going to impart more energy to these things? Making the light brighter just simply doesn't do it. All making the light brighter does is get those more electrons to come off the plate. So let's move this intensity back down to around 50%, and I'm going to change the wavelength. Remember, wavelength and frequency are inversely related, so if I make the wavelength shorter, I'm increasing the frequency of the light. So I'm going to go ahead and slide this down more towards the blue side of the spectrum. Now see how much energy that electron gets? It shoots way over here. And again, not very many of them are coming out, but the ones that are coming way, way, way far away from that plate. They're coming out with much more energy. And if I make the light brighter, if I make it more intense, you'll notice they don't come any further off the plate than they did before, but I will get a few more of them coming off the plate than I did before. They're going to come off faster, but not with any more, or more often, I guess, but not with any more kinetic energy. So this is really kind of an interesting thing. Why does changing the frequency of the light give the electrons more energy? And the way we think about it is we say, oh, well, it's because those things that are coming off of that plate, those electrons, are coming off that plate. It's because there's actually photons knocking the electrons off of that plate. Well, what's a photon? Well, it's a particle of light. And that particle of light actually has some energy. It actually has some momentum. Increasing the amplitude makes the light brighter, if you will, more intense, but it doesn't give the electrons any more energy. It's just like throwing more particles at the electrons, but not throwing them with any more energy. But when we increase the frequency, then we're throwing those particles with more energy. We are throwing those photons with more energy, which means they can hit the electrons and knock the electrons further away. And we have this relationship. The energy is given by the Planck's constant h times the frequency of the light wave. And sometimes you will see that we write frequency as nu. I do tend to use f. Alright, now one other relationship that shows us the particle nature of light is Compton scattering. This was noted by Arthur Compton, hence Compton scattering. He showed another particle behavior of light. And he didn't use visible light like in the photoelectric effect, although you can use ultraviolet in the photoelectric effect. He used X-rays. He used X-rays because X-rays have enough energy to hit electrons that when they hit the electrons, the little bit of energy that's holding the electron in the atom, in a bond, is negligible compared to the energy of an X-ray. And it just simplified the math for him when he did that. So he shot X-rays at a carbon target and measured the change in wavelength of the X-ray as it ejected an electron. Now this should make us think, a little bit. Why is a wavelength changing? If we shine a light at a mirror, we should expect that the wave, if it's a wave, it hits that, it bounces off of it, off any surface. If it bounces off the surface, it should bounce off of it in a new direction, but with the same wavelength. Reflection should not affect the wavelength of a wave. It shouldn't affect the frequency of a wave, because the reflected wave and the incident wave have the same source. They should have the same frequency. But Arthur Compton measured a change in wavelength when these things scattered off of electrons. And he was able to show, using conservation of momentum and energy, that really what happened was the X-ray ended up with a longer wave or lower frequency or lower energy because it imparted some energy to an electron. And he used conservation of momentum and energy to explain a particle of light imparts that energy and momentum to the electron. So this was a completely independent way of showing that in fact we do have a particle of light. So an incident photon, you'll notice this as a short wave, high frequency, comes in, hits an electron, knocks the electron out this way. The scattered photon goes off this way with a longer wave. It's not just reflected, it transferred some energy to it. And the amount of energy transferred we can calculate. Okay? Of course, we're familiar with the equation E squared equals mc squared plus pc squared, where p is momentum, c is the speed of light, m is mass. And so this is the energy of the scattered electron. It has momentum here. This is the energy of the scattered photon. It has momentum as well. And if we just apply the laws of conservation of energy and momentum, we can calculate this change in wavelength of this photon, which is really a change in energy of the photon. It's this particle of light that comes in and smashes that thing. So the Compton effect, the Compton scattering, the photoelectric effect, they're both particle behaviors of light, whereas diffraction is a wave behavior. So we say that it's got a dual nature. Light has a dual nature because it does. Sometimes it acts like a wave, it propagates or moves like a wave, but when it interacts with matter, it can sometimes interact like it's a particle, that can transfer momentum and transfer energy.